So good evening everyone. So we'll be starting equilibrium today. Okay. So in order to understand equilibrium first, in chemical reactions, we need to know like what are the types of reactions we have. Types of chemical reactions. So what are the types we have? Chemical reaction, one is reversible, another one is irreversible. Okay. So irreversible means that reaction will take place only in one direction, like complete completion of reaction takes place. Okay, complete reactants will convert into products. So this type of transformation we are saying it as irreversible reactions. Whereas if I say reversible reaction, when A plus B are combining, we might get C as a product. Okay, so C plus D if the products. So now what happens is, again this whatever the products formed, they will recombine to form the reactants again. So it means reaction is going backside also. Okay, so now equilibrium will be possible only in reversible reactions. Okay, equilibrium is exist only in reversible reactions. Okay, and one more thing, if the reaction is taking place for gaseous substance, it means if gases are involving, either reactants or products are gaseous. So now equilibrium reaction, that reversible reaction must be happen in a closed container. What I am saying, reaction should happen in a closed container. If it is an open container, what happens? So for example, product is gas, like C here formed is gas. What happens? It will goes out of this container now if it is open. Okay, so then what happens? Now complete reaction takes place only forward. Okay, reversibility is not possible, or equilibrium is not possible in this case, because the product formed is escaping from here. So that means reaction must be happen in a closed container if the reactants or products are gases. Okay, this is the one thing you need to remember. So now what are the types I told you? One is reversible, another one is irreversible. Okay, irreversible reaction takes place only in one particular direction. Okay, like forward direction only. Okay, now reactants are nearly completely converts into products in case of irreversible. Okay, and there is no attaining of equilibrium state in the case of irreversible reaction, whereas reversible reaction which proceeds in forward direction as well as backward direction, right now. Okay, in both sides it will be possible. Reactants are never completely converted into products. It means if I take some ABR reactants here, I am taking some 10 moles of A, 10 moles of B. Okay, out of this 10 moles, only certain amount, maybe some 2 moles, maybe some 5 moles, maybe some 9 moles, but not complete 10 moles. Okay, that only particular certain amount of reactants will convert into products, but not completely. Okay, so that is what they mention here. So attain the equilibrium state and never go for completion for reversible reaction. Okay, so these are the lines you need to know in order to understand equilibrium reactions. Okay, now types of equilibriums. So we have two types of equilibrium based on the physical states. I can say physical equilibrium, and based on the chemical substances involving, I can say chemical equilibrium. For example, a phase transition is there. So water can exist in liquid state and can also be gaseous form, right now. So now this is a scenario we will be seeing at its boiling point. So this will be the scenario at its boiling point of water. So if I heat it up to 100 degrees Celsius, what happens to the water? So liquid water converts into gaseous phase. It means there exists an equilibrium between like water liquid state and water solid state. So now these are only physical states are involving now. So we can say that type of equilibriums as physical equilibriums. Okay, so now there are some chemical equilibrium. It means chemical transformation is taking place. For example, ammonia formation. So N2 plus 3H2 gives rise to 2NH3 we will be writing. So what happens during this Haber's process? First of all, there is some amount of ammonia is formed. After that, what happens? Ammonia formed here will decompose to give the starting materials like reactants here. Okay, this is a reversible reaction where chemical species are involving here. Here in the first case, only physical states are involving for water and liquid phase and gaseous phase. I hope you got some clarity what exactly physical equilibrium and what exactly chemical equilibrium means. Okay, right. Okay, now chemical equilibrium. So when I say now we are studying about chemistry, means chemical reactions we need to know here, right now. Okay, so now during the chemical reactions, if I say reaction is attained equilibrium, it means For example, again I am taking this basic A plus B equation only. A plus B gives rise to C plus D. This is a equilibrium reaction I am saying. Okay, so now there is a term called rate of a reaction. I am indicating with R. Okay, so rate of a reaction, it means with what within the time how fast a reaction is taking place. Okay, it means if this A and B are combining and moving forward, so what I can say, that will be rate of forward reaction I can say. So with what is the fast what is the rate of a reaction means with how much fast reaction is moving forward. Okay, within some certain time. So rate of forward I can say if reaction is moving forward with some time. Okay, and how fast products are combining to give back our reactants, that I can say rate of backward reaction. So RF and RB. So now this rate depends upon the concentration of reactants. For example, see, for forward reaction, what are the things involving? Initially when we are starting the reaction, what do we have at initial time? During the reaction starting time, we have only reactant molecules right now. So then after some time only reactant molecules will be there with some concentration right now, but after some time t, what happens, some amount of product will also be formed. Right now some amount of product will be formed. Okay, so now how much amount we don't know, but that is coming from where? Starting materials only. So I can write C minus some X amount is consumed, that is C minus some X amount is consumed, that is formed this side like this. Can I write it like this? Some amount of reactants are converted into product, that X is the amount of reactants converted into products. So how much, what is the concentration of these products now formed here? X. So now this X amount of products will combine back to give like this starting materials right now. So now with what rate the reaction is moving forward is depends upon concentration of initial materials. For forward reaction, what is the things involving here, tell me? This A and B now. So rate of forward reaction depends upon concentration of reactants, concentration of A and concentration of B. Okay, similarly if I say rate of backward, see RB, so now reaction is starting from here now, this side now, so backward means from C and D it is coming back side. So it means what are the reactants for backward reaction? It will become CD. So I can say concentration of C and concentration of D. Okay, so now what happens, sometimes there will be some coefficients here. For example, during the reaction, some 2 moles of A, some 3 moles of B is combining to give some 3 moles of C and 2 moles of D, something like this they will be giving. Okay, as per the balanced equation I am saying. Okay, so now in the previous case, what you have written? Ammonia you have written. So what are the stoichiometric coefficients here? We have 1, 3, 2 like this. Okay, similar to this, here also I am writing like 2, 3, something like this. So what is the stoichiometric coefficient of A? 2. So you should write it as a power to that particular reactant. And what is the stoichiometric coefficient of B? 3 here. Okay, you should write here 3. Like this, you need to write rate of forward reaction means, rate of backward reaction means. Okay, so this will be the scenario. When this will be the scenario? If the reaction is an elementary reaction. Okay, so now I will tell you one more thing here. Okay, here at equilibrium, what happens? At equilibrium, what happens is rate of forward reaction will be equals to rate of backward. It means RF and RB will be equal. Okay, so now I am removing this proportionality. Pranita, Sanatani. Good evening everyone in the chat box. Yes. Okay, so now tell me what I can say. Rate of forward means it depends upon the reactant materials right now. So now I am generalizing these coefficients as, instead of taking 2, 3, I am just making them as some terms here, some A, B's I am taking. Okay, so like small a represent the coefficient of capital A, reactant A, small b represent coefficient of B, and here this is I am taking some P and here I am taking Q. So now what I should write? Rate of forward will be equals to concentration of A to the power A, B to the power small b. And here also I should write concentration of C to the power P, concentration of Q, D to the power Q. Like this we can write, and I can remove this proportionality, okay, and I can keep a constant. Okay, so rate of forward reaction RF is equals to forward reaction, that constant I am saying Kf, okay, into concentration of A to the power A, B to the power B. Okay, and for this reaction I can, this equation I can write RB equals to Kb concentration of C to the power P, D to the power Q. Like this we can write now, right? So now what I am saying, at equilibrium the rate of forward and rate of backward must be equal. Okay, what should be equal? Rate of forward and rate of backward. Okay, so it means that is nothing but RF, in the place of RF I can write this thing now. So Kf into concentration of A to the power A, concentration of B to the power B is equals to concentration Kb into concentration of C to the power P and D to the power Q I can write. Okay, so now what I am taking is, I am taking the ratio of two things like Kf by Kb. So what I can write, Kf by Kb means that is nothing but Kf by Kb. It means concentration of C to the power P, D to the power Q, and I am sending this there, concentration of A to the power A and B to the power B. We will get something like this now. So here both are constants, Kf and Kb both are constant. This Kf means forward reaction constant, backward reaction. See, constant, the ratio of two constant will be again a new constant, right now. So that new constant I am saying it as Kc. So now what is this Kc? It should be called as equilibrium constant. So equilibrium constant is what? Kf by Kc. Rate constant for forward by rate constant for backward. Huh? No, it should not be like always, it should not be 1. See, what I am saying, rate of forward and rate of backward must be equal. I am saying rates, I am not saying concentrations. What I am saying, rates are equal but not the concentrations. These concentrations may or may not be equal.
Coefficient also.
Coefficient, these coefficients you will get from a balanced equation. These constants, these constants also depends upon individual reaction. Okay, okay. So now, do you got this what I am saying? Okay. So now, most of the cases, Kc, equilibrium constant Kc lies between two numbers. So one is 10 power plus 3 and one is 10 power minus 3. It means Kc, equilibrium constant, will be greater than 10 power minus 3 and less than or equals to 10 power plus 3. So equilibrium constant value will be in the orders of this thing for a reversible reaction, most for a equilibrium reaction. Okay, so this will be the thing you need to remember here. Okay, after this, see, we got Kc here. Okay, so what is this square bracket indicates? This is nothing but concentration. Okay, so we can call this particular derivation, all these things, as law of active mass equation, law of active mass equation. Okay, so now what is mean by law of active mass? See, active mass is the amount of substance this completely reacting, reactant is involving and product is forming here. Okay, so simply I can say Kc is nothing but, equilibrium constant is nothing but concentration of product to the power its coefficient and concentration of reactant to the power its coefficient, whatever it may be. Okay, is that clear or not what I am saying? Yeah. So for example, reactant R is there forming some product P having coefficient here Q and here some P is there, coefficient small p. So what you should write? Kc means for this equilibrium reaction. Reactant R is there now, so Kc will be equals to concentration of R to the power its coefficient P and concentration of capital P to the power Q. That's it. Is that clear or not?
Yes.
Right. Okay.
Constants.
Constants. See, here do we have constants here? Kc is nothing but ratio of two constants.
Yes.
Okay. So just go through everything once again if you want. Got it? Right. Okay, next. Okay, so now I will ask you one question. See, for example, I am just asking you to write for this particular equation. What is Kc? So write Kc for this. What we should write? Kc is nothing but equilibrium constant.
And doing brackets. Concentration of nitrogen.
Concentration of product by concentration of
The reactant by product.
concentration of product by concentration of reactant. What is like product here we have NH3. So concentration of NH3 to the power 2 and by concentration of N2 to the, what is the coefficient here? 1. Okay, and concentration of H2 to the power 3. Like this. Whatever the coefficients we have, we should write. Okay. Now at equilibrium state they will give some values of concentration of product and reactant. So that we need to take and substitute here in order to get the equilibrium constant value. Okay. And next thing is, you know, chemical equilibriums are in dynamic in nature. What I am saying, these are in dynamic in nature. So what do we mean by dynamic here? First of all, see, have you ever observed the escalator in the malls or anywhere? Escalator. Okay. So now what happens? One will be goes up and same thing other will be comes down. Okay. Something like the process will keep on continuously taking place, but the value becomes same, that value remains same. So whenever I told you dynamic in nature, equilibrium is dynamic in nature, chemical equilibrium is dynamic in nature means, so reactants will come like keep on converting into products. Okay. And similarly products are also keep on converting into reactants. It means at equilibrium state concentration of reactant and concentration of product will remains constant. I am not saying same, they remains constant. They may or may not be same. Okay. So if you say at equilibrium concentration of reactants and products are same, that will be a wrong statement. What I am saying, at equilibrium state concentration of reactant and product will remains constant but not may or may not be same. That depends upon individual reaction. Okay. So what is the statement you should remember? At equilibrium state only rate of forward and backward will be remains same but not or may not be their concentrations. Okay. So you can expect a question based on the statement type questions based on these concepts here. Okay. So what you should remember, concentration of reactant and product remains constant but rates must be equal at equilibrium state. Okay, this is what you need to remember. Okay, so now you need to represent in a graphical way for the equilibrium reaction. So what I told you, for example, there is a reaction, initially reactant will be there, product will be, see at time t0 initially what we have, only reactant will be there but product concentration will be 0. After some time what happens, equilibrium may attained, so when, so this some amount will be converting from here to here. Okay. So at equilibrium reactant concentration is how much? C minus X. Product concentration is how much? X. These values remains constant but not the may or may not be same. Okay. So now initially what we have during the reaction at a time t0, at initially what we have here, I am taking time on this axis. Okay. At initially what we have at a time t0, we have only reactant concentration, product concentration is 0. That's why at 0 I am starting the concentration of reactant from here but product concentration is 0. Okay. That's why rate of backward is starting from down, rate of backward is starting from, rate of forward is starting from maximum. Okay. This is a maximum concentration of reactant here. Okay. As reactant moves forward, I mean reaction moves forward, what happens to the concentration of reactant? Decreasing. Concentration of reactant decreasing. It means this will remain, this will come like this, right now? Like this, come now, like this, rate will comes like this, okay? So now rate of product will also be, rate of backward also increases here, okay, as concentration, as time goes on, okay? So now we'll attain a state where this is a state where rate of forward and rate of backward are same. So what it is? Rate. Now one more term is there, concentration versus time. So at equilibrium, what I told you, concentrations remains constant. At equilibrium, concentration remains constant, but they may or may not be equal. See, look at here, do they equal? No. Concentrations are not equal, but see, after crossing this point, their concentrations are being like constant. See, they have a fixed value after reaching this point, right now? So it means after crossing this point, reaction is at equilibrium. So they will ask at what point the given graph represents reaction is at equilibrium. So whenever you are seeing constant concentrations, from that point reaction is in equilibrium.
Or when the lines are parallel also.
When these are parallel only, no? From here, from this point, okay? So do you got the difference? See, concentration means it must be something like this. Rate means must be like this. Rate should not be like this. Rate should be equal.
So what is the point of intersection?
See, this is a point where they might got equilibrium state, but very small time. After just after few minutes or few seconds, whatever may be, it got disturbed. It is increasing again. Okay, we cannot say here it is in equilibrium. Okay, it might be the equilibrium point, but it is not a stable one.
For some reaction, it may be the equilibrium.
Yeah, see, if it is constant like this, then I can say it is an equilibrium, but it is not like that now, it is changing. Okay, so this is a point where we have constant concentrations.
It should be parallel.
Yeah, that's it. What it should be parallel? Concentration should be constant or parallel. Okay, is that clear? These two graphs. Okay, you can write these two graphs. Okay. Okay, we will move forward. Okay, this law of mass action I have discussed. What I told you, law of mass action means rate of reaction depends upon the concentration of its reactants. Okay, concentration of reactant A to the power its stoichiometric coefficient A, okay, multiplied with concentration of B to the power its stoichiometric coefficient. Like this we need to write. Okay, for a reversible reaction we have, these are the reactants for forward reaction. Okay, you can write Kf, Rf for these reactants, and if you are starting from here, Rb should be written as concentration of C multiplied with concentration of D. Okay, see, we are taking products, not addition. You should take the products here. Okay, do not get confused. Okay, next. This is over. Okay, so now look at here. Tell me what is a perfect or proper representation of equilibrium constant for this. So concentration of product to the power its stoichiometric coefficient by concentration of reactants, like this. So we have only fourth option is a perfect representation. Okay, now tell me, see, there is something like some reactions will be there, so that reactions might be taking place in gaseous phase also, right now. For example, now previously we have seen that one, or for example PCl5 decomposes to give PCl3 plus Cl2. Okay, this is also a reaction which is happening in gas phase. Okay, so now simply if I ask what is the concentration, what is the equilibrium constant in terms of concentration, tell me Kc means what you will write first. Kc means what you will write, concentration of PCl3 multiplied with concentration of Cl2 by concentration of PCl5. This is how you will write Kc. But I am asking, reaction is taking place in what state? gaseous phase. Okay, so now here concentration, do see here it will be expressed in terms of their partial pressure. What I am saying? Partial pressure, not these concentrations. Okay, we can express in concentration terms also, but they sometimes they will ask Kp. Kp means what? When I say Kc, equilibrium constant in terms of molar concentration. Now if I say Kp, equilibrium constant in terms of partial pressures. So now same whatever you have written here, similar way you can write. So you just need to say partial pressure of PCl3 multiplied with partial pressure of Cl2 divided by partial pressure of PCl5. That's it. Like this. If there is any stoichiometric coefficient, just whatever the steps you are following here, you just take here also. Like if it is 2 here, what to do? PCl5 power 2, partial pressure of PCl power 2, like that. Okay. Now they will ask us what is the relation between Kp, Kc. Kp and Kc. Equilibrium constant in terms of partial pressure, equilibrium constant in terms of molar concentrations. Okay. So for an ideal gas equation, what do we have? PV equals to nRT we are writing right now. So for P I can write N by V into RT. Can I write it like this? Okay. So N by V means what? Number of moles in volume. Molarity. That is molarity. That is nothing but concentration only, na? So P I can write, here I can write concentration C R T. Right now concentration we are indicating with this square bracket. Okay. So P is equals to C concentration into RT. Okay. So now simply you can see wherever I have partial pressure, I can replace with its concentration, multiply with RT. See, here I have partial pressure of PCl3. See, if I have P, instead of writing P, I can write C, mean concentration multiplied with RT. Okay. Here I am saying partial pressure of PCl3. It means what I can write? In the place of P, I can write a square bracket here. It means that is nothing but concentration of PCl3 multiplied with RT. What is its power we have? 1 na? So here also 1. Okay, no need of writing that. Okay, next one is PCl2. It means what I should write? Concentration of Cl2 multiplied with RT. Okay, if there is any power here, you should write that power here. Okay, next in the denominator what we have? P, partial pressure of PCl5. Okay, that is nothing but concentration of PCl5 multiplied with RT. That's it. Okay, so now substitute these values over in this equation. What we will get? So we will get something like this: Kp equals to Kc RT power delta Ng. What is this delta Ng here? See, why I am getting this equation? First, if you want, we will make each step again. Okay, so Kp means what I should write? Partial pressure of PCl5 in the PCl3. In the place of that, I can write this thing. So I can write concentration of PCl3 multiplied with RT, and the next PCl2 I have, Cl2 I have. So partial pressure of Cl2 means I can write concentration of Cl2 multiplied with RT. Again here I can write concentration of PCl5 multiplied with RT. Like this I am writing. Okay, so this RT can be cancelled out. Okay, so Kp is nothing but these are concentrations now. So if I write concentrations aside, we will get this equation. That is nothing but Kp equals to Kc multiplied by RT. How many RTs are remaining? 1 RT. So write like this. Okay, now in a simple way we can make a formula for this Kp Kc relation formula we can make here. So Kp equals to Kc RT power delta Ng. So what is this delta Ng? Delta Ng represents number of gaseous, summation of number of gaseous products minus number of gaseous reactants. Okay, summation of number of gaseous reactants. Only gaseous things we should consider in order to calculate delta Ng. Okay, for example, same reaction you directly tell me here PCl5 is in equilibrium with PCl2 3 plus Cl2. So tell me what is Kp Kc relation for this? Kp equals to Kc RT power, how much we will get? See, all of these are in gaseous state only. Then what happens to the delta Ng? Tell me. Delta Ng should be taken as, how many gaseous react products are there? 2. 2 is like 1 plus 1, 2, minus reactant is 1. So it will be 1. Delta Ng is 1. So wherever we have delta Ng, there you put 1. That's it. So Kp equals to Kc into RT. That's it. This will be the equation. Now during the exam, they might ask you directly what is Kp Kc relation, or they will give you the value of Kc or the value of Kp. Any one value they will give at some particular temperature they will give. So what we need to do, if they give Kc and temperature value, you can put R value over here, substitute them, and you can get the Kp answer. What is the value of Kp? Okay, like this they will give the data of something and they will ask for the unknown thing. Okay, from this relation. Okay, so what is relation between Kp Kc?
Kp equals Kc into T
Power
of N
delta Ng. That's it. Okay, now tell me your answer for this question. The value of Kp will be equals to Kc in which case? You can able to answer easy. So those who are in online, you can also answer if you know that. Just write it in the chat box. So what to do? Just find Kp Kc relation they are asking. So what to do? RT power delta N. Just find this delta Ng value. If it is 0, then this whole term become 1, then Kp equals to Kc. That's it. So here delta Ng is how much? 2 minus number of gaseous product is 2. Gaseous reactants also 2. So 2 minus 2, 0. So in this case delta Ng is becoming 0. So it means something power 0 will be 1 right now. So this whole term become 1. So Kp will be equals to Kc in first case. Tell me in second case, that will be equals to Kp equals to Kc RT power 1. Next in this case you tell me Kp equals to Kc RT power 3 plus 1, 4 minus 2. So 3 minus 4 minus 2. So this will be 2. So RT square will get in the third case. Okay, fourth option you tell me? Minus 1. So it means Kp equals to Kc into RT power minus 1 right now. So instead of giving like this, they may also give Kp equals to Kc by RT, or they may also give Kc equals to Kp into RT. Any of these 3 ways are correct only. Okay, all these 3 ways are correct only. Okay, right. Let us move forward. Next, remember what to remember here. At equilibrium, all macroscopic properties such as pressure, concentration, we already discussed about concentration, density and color will be remains constant. Okay, all these properties will remains constant. It means, for example, I will explain about color here. For example, reactant have no color, but product is having some color. So let us say what color we'll take, some red color we have for the product. So now what happens? Reactant initially for the reaction there will not be any color at a time t0. Okay, so will not be having any color for the reaction because this is colorless now. Okay, colorless I am saying, reactant is colorless, only product is red color. So at time t0 initially we have only reactants, product will be 0. After some time t, what happens? Some of this will be converts into product form. It means as product is forming, the intensity of color of the reaction will what happens? Intensity of color of the reaction increases because red color is slowly forming now. Okay, and we will reach a point called equilibrium point. The color intensity of the reaction will remains constant. That red color appearance will remains same. Previously it is slowly it converts into pale red to red like that, dark red like that, it will goes on increasing. Once it is attaining equilibrium, that red color will remains, that intensity of red color remains same without changing its any of this intensity of the color. Is that clear? What do we mean by these things here? Right. Okay. So now what I am saying, chemical equation is in, chemical reactions are in dynamic, static and dynamic. Static means there is no change, like it will remains constant. But dynamic case, what I told you, the amount of reactant converted into product at the equilibrium, same amount of product will converts into reactant. Therefore, net change will be 0. Okay, it means concentration of reactant and product will remains constant.
Yes. So in static there will be no rate.
Static means there is no mobility, I can say.
No rate.
Rate is there, everything will be there, but concentration of reactant and product will remains constant. It means there is no mobility, but here mobility is there. For example, this classroom is having 2 doors, consider here and here. Okay, for the person going from one door from here, let us say he is the reactant. Who is entering from here will be the product, let us say. So if 2 persons are going out, at the same time 2 persons from outside will come in. It means what? The net change will be 0. This is what the dynamic means. So this happens, keep on happening at the dynamic equilibrium means. Static means there is no change in that way. Whoever the person staying inside, they will stay here. Whoever person staying outside, they will stay there. That is what the static.
No flow.
No flow, yeah. That is what no mobility or no flow I can say. Okay. Next. Yeah. So tell me, KPKC, this is NEET 2024 question. Tell me what is the relation here we have? Yeah. So someone asking in the comment box, sir, organic, when will you start? So actually for morning batch, organic is already started, it's going on for morning batches. As of now I am discussing GOC part. Okay. So today I have covered till conformations. Okay, like Sahar's projection, Newman projection, how can we convert them one to other forms. Okay, all these things are discussed very clearly, and if you wanted to join, you just contact to the mobile numbers given here in the description box. Okay, you just message or our team will contact you back. Okay, so for this evening batch we will start after a few more days. Once after completing equilibrium we have redox. After redox we will start GOC, organic, IUPAC nomenclature and all. Okay, right. Okay, so tell me here, KP, KC are not equal in which case? Easy again. Here delta Ng is 0, it means that is equal. Here delta Ng is not equals to 0, it is 1. So this is not equal. Okay, this is the answer. What about here? It is delta Ng is 0. It means it is equal. What about this? 0. Delta Ng is 0. So it means option 2 will be the perfect answer here. Okay, right. Next. So now there is something called characteristics of equilibrium constant. So what are these characteristics? Few things we will discuss today and remaining we will discuss tomorrow. Okay. So now first thing is, if an equilibrium reaction is see, first of all you write this thing, first of all this is a very basic thing. Equilibrium or the value of equilibrium constant, the value of equilibrium constant remains same, okay, by change in concentration or volume or pressure or density, whatever it may be. Okay, so this will remains value of equilibrium constant value remains the same by changing any of these things. Okay, but if temperature is changed, the value of equilibrium constant changes. What I am saying? If concentration, volume, pressure are changed, the value of equilibrium constant will remains same. But if we change the temperature, the value of equilibrium constant changes. Okay, so in order to understand this statement properly, we need to learn Chatelier principle. That will be discussed in the next class. Okay, so what we need? Chatelier principle is very important. There we will get more clarity on this particular first statement. Okay, okay, and next thing is if the reaction is multiplied, if an equilibrium reaction is multiplied by some number n, then its new equilibrium constant will be Kc to the power n. It means what? For example, a reaction is taking place between A and B. Okay, so what we will be writing here? So we will be taking Kc as an equilibrium constant for this reaction. Okay, how you will write Kc for this reaction? Concentration of B product by concentration of A reactant. That's it now. Now what I am doing? I am multiplying this particular equation with some number 2. Okay, what happens? 2A gives rise to 2B. That's it now. Then its new equilibrium constant Kc dash I am saying for this. Kc dash will be equals to concentration of product to the power its stoichiometric coefficient 2 and concentration of reactant, that is A, to the power its stoichiometric coefficient 2 here. Okay, it means what happened here, what you have seen here. So Kc dash is nothing but Kc to the power 2. That's it now. See, these values I can take from here. Okay, it is nothing but Kc to the power 2. Yeah, that's it. Okay, common you take for square. Okay, so now same reaction if I am multiplying with En. So Na giving rise to Nb. Now tell me what happens to this Kc dash? What is the relation between Kc dash and Kc? So just write Kc double dash equals to, means for this Kc double dash I am saying Kc double dash equals to Kc to the power En, because we multiplied with En. That's it. Is that clear or not? Yeah. So if an equilibrium reaction is divided by En, then its new equilibrium constant will be Kc to the power 1 by N. What I am saying, if reaction is divided by N, its equilibrium constant becomes 1 by N. Okay, for understanding purpose, we will take this equation. See here, I am taking 2A gives rise to 2B. For this, I am saying equilibrium constant is Kc. Okay, so now I am dividing this equation with some number 2. What happens to this? See here, what happens? A gives rise to B. So here I can say Kc dash is how much? So simply what you can say, Kc equals to B to the power 2, A to the power 2, and Kc dash equals to B to the power B, A to the power A. That's it now. Okay, so now here I can write Kc equals to B to the power B to the power 2, A to the power 2 means I can write them like this. Okay, so now that is nothing but B by A is nothing but Kc dash, right now. So now I can write Kc equals to Kc dash to the power 2 here. But what I am asking, I am asking Kc dash. It means what it will be? Kc dash will be equals to Kc to the power 1 by 2. That's it. Okay, you just apply root over both sides, you will get this thing. Okay, I hope it is clear. Now, if a reaction is multiplied with n, tell me, Na giving rise to n, sorry, if a reaction is divided, for example, I have A gives rise to B, I am saying its value is Kc is equals to, Kc only I am saying, we will do that problematic question next step. Okay, so I am dividing this equation with n, number n. So what happens here? Tell me. Kc dash will be equals to how many times of that thing? First thing. What I should write? If I am dividing an equation with n, what happens to its equilibrium constant? Just take Kc to the power, whatever you have number divided here, take here 1 by n, that's it. Okay, hope it is clear. Now I will give you one question, tell me. A to B, Kc value is 25. Then if I am dividing this 1 by n, A gives rise to 1 by n, B. Now tell me, what is this Kc dash? I am dividing with n.
5.
Yeah, so you just Kc to the power 1 by n, that is nothing but 25 to the power, what is the number I have taken here? I am taking some number 2 here, dividing with 2. What happens? 25 to the power 1 by 2. Okay, that is nothing but root 25 is nothing but 5. So this will be the answer for Kc dash. Hope it is clear. Yeah, remaining things we will discuss in the next class. Just tell me your answer for this one question. This one question, very simple. Just look and tell me your answer. Fourth option. How it is fourth option? See, reaction is divided by 2. So for this I am saying K, for this K dash. So K dash will be equals to, since reaction is divided by 2, K to the power 1 by 2. That's it. Very simple, right? Okay. Yeah. Remaining things we will discuss in the next class. Okay. If you have any doubts, you can ask me now. Okay, or go through the textbook once, you will get more questions from there. Okay, solve them. If you have any doubts, you can ask me in the next class.